want to welcome everybody to another Noyo Center Science Talk. Thank you for joining us tonight. I'm super excited, as always. I think I say that every time, and every time it's true, about our speaker today. If you've been to the Discovery Center and you're like me, you've already purchased some of her ceramics for gifts for your family. Leila Al-Hemali is our speaker tonight, and I was telling her before when we were just chatting that the bio that she gave us has one of the best sentences that I've read in a long time. And this is that sentence. In a world where people are encouraged to specialize, Leila will discuss the need for multidisciplinary thinkers and cross-concept collaboration to find novel climate solutions. There couldn't be a better sentence to sort of, I think, not only set the Noyo Center in context to this talk, but because I couldn't agree more, but also to tell you what this amazing dynamic person is doing. So I'm not going to talk too much about your background because I'm hoping you'll do that.
Thank you for the introduction. My name is Leila. I'm very into interdisciplinary thinking. I'm a ceramicist and a software engineer. I'm into coding and clay, pottery and programming. Big fan of alliterations over here. But this talk is primarily about a project that it's been like a 2-year long artistic thread at this point, but the bulk of it happened at a ceramics residency that I did in California last summer at a very small place called Cobb Mountain Art and Ecology, about 40 minutes north of Napa Valley, but in Lake County. If you live in California, it's likely one of the only places in California you've never been. But the remoteness was awesome, awesome for some things. So I'll get launched into it. So here's just a quick overview. First off, I'm going to talk a little bit about my backstory and how I came across this project. I'll do a little bit into kelp forest decline. This is an intersectional talk, so we've got a lot of different topics to cover, but I'll do a brief introduction into glaze and glaze chemistry, which, if you're not familiar with that, it's the coating that's on the outside of ceramic pieces. And then I'll talk about urchin whiting, which is my process for incorporating urchin into glazes. And then I'll finish it off by showing some of the more exploratory pieces I made last year, all centered around trying to create in concert with the Pacific Ocean, and the really just such an amazing resource in so many regards, but there's really a big depth of pottery that I think is underexplored in working with the Pacific. So here's how I got hooked on kelp. This is a picture of me with my friend Lasra at the kelp. It was this California Seaweed Festival 2022. I was walking around with my friend on Pacific Beach, and I came across this really big, long, beautiful piece of feather boa kelp, which if you're not familiar, it actually really looks a lot like a feather boa. But they're like 12 feet long. They're waving back and forth in the tidal forces, and sometimes they wash up on the beach. And this is a couple days before Kelp Fest, and I picked up this piece of kelp and I was just loving playing with it. It has these pneumatocysts, these little air pods that are on them. And I was really fascinated just thinking, like, how does the kelp get the air into the little pot of air, these sacs that give it buoyancy to be raised up towards the ocean surface. That's why kelp is always reaching towards the sky. And then I met this woman, Lasra, and she was like, oh, I'm going to go to this seaweed festival in Tiburon in a couple days. And I was like, oh, can I come? I have a kelp question. Something in the chat.
I know it's somebody saying, I'm sorry to interrupt, somebody saying they can't see your photos. Are other people able to see the presentation? Wendy,
I can see it.
You can see it? Everybody?
Okay.
Yes.
Peggy, you can too? So Beatrice, maybe you're on the wrong, maybe you need to.
Yes.
Okay, so maybe Beatrice, it's a setting on your computer.
Okay, great. So we went to this kelp festival, and it was just a really inspiring event. It was small, and I don't know if anyone's ever been there. It was like up in the North Bay in this little like marine science area called Tiburon. Here's a picture of this woman who just is a encyclopedia of kelp, which before 2022 I didn't even know people like her existed. But she took us on a walk
That
along the
Kathy
coast.
Ann Miller.
Yeah, Kathy and
Yes,
Mil.
she just stayed at Science Talk Force too.
Oh man, took us on this like walk along the coastline of the San Francisco Bay, which is actually not the most like beautiful or inspiring environment because it's so human populated. Like I think even in some of the pictures with Kathy, there's like trash on the ground. But meanwhile, she's like going through the rocks and like picking up all these specimens of kelp and talking about them. Um, and I have this awesome sweater and it says "In seaweed we trust" in the back on the back, which has just become more and more a mantra for me over the years as I've kept working with kelp. But this event was really important to me because it's also where I learned about kelp forest decline, which I grew up in Florida. I've always been an avid diver and I've always wanted to dive the California kelp forests. And so when I was at this event, like full of scientists and artists, I was so inspired. And I was just, and they're talking about the kelp forests are going away. And I'm like, well, I haven't even gotten a chance to dive in them yet. This can't be happening. And so I was just, I guess, just kind of one of those good moments of inspiration, remembered from an earth science class I had taken that all marine invertebrates, which urchin are, their bodies are made from calcium carbonate. And as a potter, I know that calcium carbonate is something that we use in glazes. And so that kind of started my fundamental question, like, can you use the urchin calcium carbonate as a replacement for our commercially mined calcium carbonate that we use in glazes? Which I'll come back to the exploration of that later. But this was really just like, felt like one of those kind of predestined things that happen where you meet somebody and they're doing something that's exactly what you want to be doing. And it honestly, like this one day, led to like a 2-year long artistic thread for me, which I am so grateful for. Um, so here's a picture I took the very first time I was in Mendocino. It was later on in that time when I was in the Bay Area, and there was just this awesome stand of bull kelp there, and this person out there fishing it. But a lot of you all probably already know this, that in the last decade, approximately 90% of the Pacific kelp forests, which historically range from Baja California all the way up to the Aleutian Islands in Alaska, has been replaced with urchin barrens. Um, so I continually say this is a classic case of ecosystem disruption. I don't know exactly when, but a while ago, this sea star wasting disease started showing up on the California coast. And these huge sunflower sea stars, the ones that have like 15 to 24 arms, they're really crazy giant creatures. Those started dying and 2013, thank you. So also around the same time when the kelp loss started, the sea star wasting disease came around. A lot of people are studying it, but unfortunately people haven't found a cure for it yet. But when I was in Mendocino a couple months ago, somebody did say that they saw one of these predatory sea star off the coast. So like everything, it is still hopeful. I don't want to get too morose, but it's really interesting with the die-off of these sea star and then dwindling otter populations before, I mean, this is probably goes back over 150 years, like to the 1850s when Europeans first started colonizing the coast of California, particularly, I think, French fur trappers, people taking otters out of the environment and turning them into furs. The urchins do not have any main predators, and therefore nothing to fear. So I've learned this too, which I think is really interesting, is that the urchin used to hide in little crevices on the rocky seafloor. But without their predators around anymore, they have left those crevices and more just are free to roam, free to graze. It's kind of fun to think about like little sea urchins grazing across the ocean floor, kind of like a little herd of mindless cows is sometimes how I picture them. But instead of eating grass, they're eating kelp. And so it is true, it's overgrazing in the kelp forest. And kelp is just particularly susceptible to this problem because if you've probably seen it, kelp is just attached to the rocky seabed by one long stem. And so it's really easy for a sea urchin to climb up on that stem and just munch all the way through it. And so even though the kelp itself is 7 feet tall, 10 feet tall. These giant kelps get so big. It's so easy for a sea urchin to end its life cycle prematurely. Um, so this is kind of fun, and a little kind of related to my work. We do a lot of modeling of complex systems, like I was talking about with some folks earlier, wildfire modeling. And so this is a rather new programming library called AgentScript that I was like, hey, let's see if we can build an AgentScript model of the kelp forest decline. So here's my thinking is that we've got this. Imagine you're in a kelp stand off the Mendocino coast. We have 3 players. Well, maybe 4. Player 1 is kelp, which is these little green darts that are on the screen. Player 2 is the sea urchin, which are the little purple balls. And then player 3 is the sea stars, which are these orange pentagons. And then the 4th player perhaps is time, which is a huge part of these systems is time. Kelp is naturally an annual or a perennial. Two of the main kelps that make up the forest or the canopy of the kelp forest. One of them, bull kelp, it's that really long one that has kind of like a human alien like head that bobs at the surface, and it has really long stipes that always, I think so many people makes think of like mermaid hairs. So that's bull kelp, and then the other one is giant kelp, which is similarly tall, except its growth pattern, it has one long stem, and then all the way up the stem, it has a series of stipes, which is the leaf of a kelp, you could say, coming off of it, that also flutter very poetically in the ocean currents. So anyway, time is really important in this system because the kelp is dying off every year naturally. It's an annual. Bull kelp is an annual, and giant kelp, they say, lives between 5 and 7 years before it naturally ends its life cycle. But you can do the math pretty quickly. If you have no kelp to have a seeding event, then there's no seeds falling to the seafloor. There's no kelp regrowth happening. So it's pretty pivotal to the system that there aren't too many sea urchins, because while the kelp itself grows really, really fast, I think it's part of the reason why the kelp forest loss has been so fast is because it's going through the cycle that I've done a little bit of work to try modeling. Okay, so back to this model. We're starting off, we've got 500 kelps, we have 50 urchins, and 5 sea stars. And I'll say all of this is pretty arbitrary. Like this is an artistic model, not a scientific model. I'll say it that way because this has not been put up to the rigors of science. But I think it does a really good job of getting a point across. And so I chose these different numbers because they say that you lose 90% of energy as you go up trophic levels. And so kelp as the basal trophic in the system, it's what's it's what's using sunlight and turning into biomass. We have the most of it, 500, and then the urchin is 50, and then the sea stars are 5. So we'll start the simulation, and I'll just give you all a little bit of information about how they're moving. So the kelp cannot move. The urchin are moving randomly through the system until they get too close to a sea star, and then they're repelled from the sea star. And the sea stars are also moving randomly through the system until they get within one patch, which is just the size of our network in here. Then they're like, oh my gosh, there's a sea urchin there, and they take on this very predatory behavior. Like this one's really fun to watch. He's getting a lot of them, and become a lot more aggressive in that moment. And then I also have this every 365 steps of my model, everything repopulates, but only based on how many urchin there are and how many kelp there are. So if there's only one kelp, there's only one kelp that's going to repopulate. So this, perhaps my initial model really isn't that healthy of a system because, as you saw, the sea stars totally started taking over, which I did not program in a death rate for the sea stars, which, I hope to iterate on this. But let's restart it. And then let's just see really quickly, we have this year incrementer here, how fast the urchin can totally decimate a kelp forest. And this is just, again, these urchin are kind of stupid, like they're just moving through the system, and when they find kelp, they eat it. Now we have a ton more sea urchin now that we don't have the sea stars preying on them. Um, and we also have a ton more urchin eating kelp. And so this was, yeah, I didn't even get to year 2 in my model before the urchin ate all of the kelp. So this is kind of just a quick, like, this is thinking about predator-prey interactions, this is thinking about repopulating, um, and it's kind of fun just to be able to quickly put in different amounts of sea star and urchin and kelp and kind of gamify the system and start looking at, how quickly these ecosystems can change, especially fringe ones like the kelp ecosystem. Cool. Yeah, and now my screen's in full screen again, right?
Yeah, you're good.
Okay, cool. So a lot of this project has had me just kind of waxing poetic, thinking about sea urchins and their role. And I think I don't know if it's a coincidence or not, or how this came to be, where the word urchin has this dual meaning of being this sea urchin, this actually like pretty adorable, beautiful, interesting creature. And we also will say like an urchin as, kind of this derogatory term, somebody who's like feeding on detritus is maybe where it came from. Um, but it's kind of just raised this question in my head, like, are we the urchin in this big earthen ecosystem? I think as somebody who's been into conservation for a long time, I've also oftentimes felt really embarrassed to be a human, because of how much damage, or I guess changes we've made to our broader ecosystem. And this is honestly like humanizing the urchins have like helped me humanize myself and humanize the whole world population, because when you watch them move through the system, they're really quite clueless and they're really just trying to do what they have to do to survive. Um, and that's been just a nice kind of reconciliation. um, of okay, well, the urchins did completely eat the kelp forest, but they also didn't really know what they were doing. They didn't mean to. They were just moving through the system and taking the opportunities that were in front of them. Like, I also feel humans are very opportunistic, the same way sea urchins are. Um, and so I think it's been kind of a dual process throughout this project of like finding some more love for myself as a human, while I also try to find some love for these sea urchins, who are, at the end of the day, totally devastating the kelp forests, but also are just trying to survive. So this is where I'll get sciencey for a minute here. Um, so um, this is how calcium carbonate is made. And so like I said before, urchin and all marine invertebrates, so including sea stars, mollusks, their bodies are made from calcium carbonate, which it's found in a lot of different places, pretty much in any marine environments. There's a lot of calcium carbonate around. Even coincidentally, my company, we use calcium carbonate as a replacement for silica-based sand on the sand tables that we ship. Um, but there's this whole kind of constant constant chemical interaction going on in the ocean, which this is a graph I pulled because it's talking about ocean acidification. But it also does a really good job of showing what chemical processes we're looking for. So basically, there's obviously water in the ocean. Carbon dioxide dissolves really easily into water, and creates this carbonic acid, which then you need for to have these carbonate ions, which the sea urchin and all the marine invertebrates, they are fixing calcium and they're fixing carbonate out of the water and they're turning it into their calcium carbonate bodies. Um, which this is a little bit tongue in cheek, but as ocean acidification continues, we're gonna see this interaction happening less and less, and it's gonna be harder for marine invertebrates and corals to make their bodies. And so, with absolutely no intervention, there is a world where the urchin barrens don't even form anymore because the ocean has become so acidified that even the urchins can't form. And then I don't know, maybe kelp will come back on its own if it's able to grow in a lower pH ocean. Kind of an interesting research topic. I would love to see somebody write a paper about if the ocean will become so acidic that the urchins die off, but the kelp comes back. But that's not what we want. We're aiming for kelp and urchin to live in harmony as they have for a long time. Um, so here's the part of my talk. What we're gonna get into some pottery now. So keep everything, it's all gonna come back together. Just keep it all in your mind. We're gonna jump from ocean acidification to what is a glaze. And a glaze, the short answer is it's crystals. I have a bunch of different pots. These are the ones that I was selling at the Noyo Center. But a glaze is this white surface. It's not this. This is just the raw clay body. But pretty much always when you buy ceramics that's been handmade and machine made, it'll have this glaze on the outside of it. And so this is really interesting, probably more so to people who are potters. But the short answer is it's a crystalline network. And so we as potters were making these mixtures of all of these different minerals that we know are gonna melt when we put them in the kiln when we fire them. Um, and so it's a crystalline coating applied as a finishing surface effect on ceramic wares. It's often glassy. And you can break down glaze chemistry to be really simple, but there's also like volumes and volumes that can be spoken on this topic because we're really one thing I love about ceramics is we are taking the earth's processes and we're putting them into a microcosm and we're speeding them up or we're making them happen on our timelines. So this is all where it kind of starts to get mixed in with geology here. But clay, which again, a huge topic of what actually is clay. Um, but it's just the same type of clay as we're calling clay to make the piece. You need a little bit of clay in your glaze. You need a fluxing agent, which is something that helps all of the other minerals melt at a desired temperature. So you can just think of a fluxing agent really simply as something that lowers the melting point of everything else that's in the glaze. And then people usually add a colorant, which is something that gives it its characteristic. You can make white glazes. Here's a blue cup that I've made. I have all of the different urchinware cups. That I'll show in a little bit. But those are usually metal oxides. And a lot of times those metals that the like alkali earth metals like sodium, potassium, magnesium, those are things that can really easily take the place of silica in its crystalline structure, therefore causing impurities, which then cause them to be optically different colors. So, like ceramicists know, usually when you add potassium to a glaze, you're going to get kind of a greenish crystalline form. If you add sulfur to a glaze, you're going to get kind of a yellowish crystal. Calcium also will show up as green. Magnesium a lot of times shows up as purple. But it's kind of like paint, but there's a lot more chemistry behind it. Where over decades and decades, thousands of years of people making pottery, people have learned like, okay, sources that have magnesium, those glazes end up being purple. And you can take them, from natural sources, these colorants, but a lot of times you can just buy metal oxides like at your local pottery distribution store. And then the last bit of what is a glaze is you need a silica source, and that is our glass former. And so silica, which a really great source of silica is beach sand, is it's pretty much what all glass is made of. I'm pretty sure SiO2. But that forms glass, it melts, it solidifies, it creates a continuous surface. And then we are looking for what makes a glaze interesting, usually is these colorants that you can add in that will make it have different colors. Different amounts of flux will make the glaze kind of run some and give it some texture in that direction. I have lots of pictures I will share in a minute. So now I'll get into kind of more of a narrative. Let me see, does anyone have any questions at this point? This is like a good, I'm gonna move in away from so much science stuff.
Don't forget, if you have a question, to unmute yourself. Everybody's been very good about keeping themselves muted.
I have a question. Hi,
Hey, Margaret.
good to see you again. I was wondering with the urchin glaze, can you add the colorant? Like you said, I think sulfur, you can make it green. How does that work to make a colored urchin glaze?
Yeah, that's a great question. So I guess I honestly didn't try coloring it with pure metal oxides. So I think that's a good place to mess around with stuff. I did color it with these things called mason stains, which are kind of a newer introduction into the pottery world. Which is how I made this. I made just a purple one, this urchin purple. Is the introduction of a mason stain into the urchin white. Um, but I think with the metal oxides, you probably would just want to work at a higher temperature than a lot of these pots than like the classic urchin white is. So this is another kind of thing about pottery is we work at different temperatures. And so there's cone 6 is a really common temperature. It's called mid-range. And then cone 10 is high fire. And actually between those two distinct places, there's only like 200 degrees Fahrenheit difference, but they cause a world of difference in ceramics, which is just so amazing. So I think go for it, Margaret. Like get some metal oxides and mix it in with the urchin white and then just see what happens. A lot of times you want to be working at a higher temperature to work with them, which my urchin white is a cone 6 glaze. So I'm not sure it'll work, but it really might. It's really just, people have been making beautiful pottery since before we had any idea really what was in clay. Exploration and experimentation has definitely been how all of the methods that we use now and understand how they work. It's because somebody developed them and then we like reverse went into the science and we were like, oh, like this is why this clay has this color and this is why we're going to talk a little bit about wood fire pottery. Wood fire pottery is one of the oldest forms of making high fire glazed surface pottery. And then people went back and realized, oh, the wood is doing this. And that's why I can name specific cations as this makes this is because people have explored for a long time.
I have could I
Yeah.
ask a quick question? This probably shows that I didn't understand what you were saying earlier, but um, what what is how come the glaze is not purple from the color of the purple urchin? What happens to that pigment?
Yeah. So I really want to use a scanning electron microscope to go deeper into what's really in the urchin. But I think it's just calcium carbonate, and that what makes it look purple to us is an organic compound that burns off at a much lower temperature. So early on, when I was exploring this process, I was calcining the urchins. I was firing them to a low temperature, less than 100 degrees Fahrenheit, just to make the bonds more brittle, to make them easier to crush up. And I would put purple urchins into the kiln, and then when they came out, they would already be gray. So whatever makes them look purple to us, I think is organic because organic compounds tend to burn off at a really low temperature, is probably something that the urchin is making itself. It's really, really, that's like another whole research, somebody's dissertation needs to be like, why is some urchin purple and why is some urchin red? And what is actually doing that?
Yeah,
Because
so I don't know the chemistry behind it either, but what's really interesting for most people to understand is that urchin have a skin. The purple is the skin of the urchin. And so if like when we see the cannibalism in our raceway system, with one urchin eating the other, they're eating the skin off and the test underneath is green. So we call the test a shell, but it's really not a shell, it's an exoskeleton, right? Because they have this layer of skin around the outside of it, and that purple is I don't know the chemistry either behind it, but that is
that
their,
is so interesting.
yeah.
I did not know that. That's really cool. Yeah, they're amazing little creatures.
They are, and I'm
not
glad
having
you're
brains.
taking that. We're trying all the time not to get people to vilify them because they are super adaptive.
Very cool. Very, very cool. Okay, so I'll start talking about my residency. So as I mentioned earlier, last summer I was in Lake County at the Cobb Mountain Art and Ecology, which is just a really beautiful, really intentional facility. So the person who runs it, Scott Parody, he's got about 80 acres of land that is forest that has not been particularly well maintained. It used to be owned by a logging company before he bought it. And so he's been going through the process of kind of helping the forest get healthier. He does prescribed burns on his own land every year. And he also is a really passionate wood fire potter. And what part of the process and part of the residency is going around the property, helping clearing excess wood, and then taking all of that wood and chopping it up and using it as fuel to make our pots. So here's a picture of the main studio building. Just a lot of really fantastic. If you're ever 40 minutes north of Napa Valley, definitely go check it out. I think you just have to email him beforehand, but there's really fantastic ceramic wares up there. And then also kind of the flagstone of the property is this huge 30-foot long onagama kiln. Which, I mean, there's probably only 12 of these in the country. Like, they're really, really special kilns. It takes days to load them. You put thousands of pots in. And then with a team of like 25 other potters, we were firing it for about 10 days until it got to 2,500 degrees Fahrenheit. And this is early on in the firing. You can just see all of the crates of wood that we're going to go through throughout the course of this firing. Let's see. Here's the interior of the kiln. But my residency while I was there, I had two main focuses. My first was using the urchin as a replacement for commercially mined calcium carbonate. And the second was exploring incorporating other elements from the kelp ecosystem into my pots. So I had this kind of like very focused, like, okay, we're gonna look at something that's commercially viable. And then this other, like, we're just gonna explore kind of thing that I was doing in tandem the whole time I was there. And so the first is processing urchin, which actually really wasn't that hard. It was like I had this idea, and when I finally acquired my first sample of urchin, which I was like cold emailing people who worked like in urchin fisheries, and eventually Josie Islin, who is probably another great friend of the Noyo Center, she just like sent me a box of urchin tests that she had gotten to scan. And it was really easy to crush them up and get it all to work. Like, I really honestly was like, the first time I was like, okay, we're gonna go in, we're gonna crush up some urchin. I was like mentally prepared for like months of rigorous testing and taking notes and tweaking this recipe and blah, 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 and all this. And it totally worked on the first try. So it's pretty simple. So whiting, which is what we call it in pottery, is the same thing as calcium carbonate, which is the name of the mineral, is the same thing as CaCO3, which is the chemical formula, is the same thing as limestone, which is really where we get our whiting from. So I'll say this now. Limestone, which most often is compacted and lithified seashells. So calcium carbonate does naturally precipitate out of the water, but also a huge way that calcium carbonate and limestone is getting made is these marine invertebrates doing that same, marine invertebrate magic that I showed on a couple of slides ago of fixing calcium and carbonate out of the water and turning it into calcium carbonate. And then when they die, they just sit on the seafloor. Coral beds do this until like gradually over time, I mean, we're talking hundreds of millions of years, they all get compacted and then lithified and become limestone, which then later gets uplifted in other geologic processes. Like the entire bedrock of Florida is just all limestone. Which something really amazing about doing this project is just thinking about bypassing hundreds of millions of years of geologic time. And just, I have whiting that's from a commercial source from limestone, and then I have whiting that's derived from sea urchins, and they're actually the same thing, but one of them is 300 million years old, and one of them is a sea urchin that maybe was born last year and now I have in my hand. Really crazy to time travel through the science like that. So as potters, we put calcium carbonate into our glazes so that it can decompose into calcium oxide. And what that does is it works primarily as a flux, which is something that's a melting agent in our glazes. But it also can add a matte characteristic in high enough quantities, which is part of my thinking in choosing this particular glaze was I was like, how can I use the most sea urchin possible? And that's why all of the like traditional urchinware glazes are matte, is because I just wanted to put a lot of calcium carbonate into my glaze. So oh yeah, and here's a picture. This is the calcium carbonate as it is when I add it into a glaze. So this is sea urchin right here. It's just been crushed up into a really small powder. And here's about how I process urchin. This was taken at a workshop I taught at the Mendocino Art Center a couple months ago. But really, it's just the best picture I have of me with my trusty grain mill. So this grain mill, I bought it off Amazon for probably $30. It's like the same thing that probably your grandma or your great grandma would use to crush up corn in her kitchen, just mounted to a little piece of wood so that I can apply a lot of pressure to it. And that in itself is enough to mill calcium carbonate down to the right particle size that we need for glazes. That's something that I'm just really grateful for about calcium carbonate, is that it's a really soft rock comparatively. So I didn't have to go through this huge process of figuring out how to actually mill something to be really small. That's something that people usually use like really expensive commercial equipment for. And I was able to do it with this like little grain mill that I bought off Amazon, that I still have and is still serving its original purpose. And I mentioned this earlier, when I started this project, I was calcining the urchin. Like I was firing it to a really low temperature because I wanted to like just kind of pre-break it up a little bit, like hoping that applying heat would break up some of the bonds. Not like the calcium carbonate itself, but just like the calcium carbonate to calcium carbonate bonds. And I ditched that process. I ditched that part of the process later on for two reasons. One, because I realized I don't need to do it, so why would I do a step that I don't need? And then second, when I first started getting urchin, they weren't fully decomposed, like all of the organic bits on it. So when I was calcining it, I was also burning off the like the organic parts of the sea urchin, which is just like the most disgusting smell I've ever smelled, like this like black billowing smoke coming out of the kiln of like burning urchin bits. So I was really, really grateful when I came to California and someone was like, oh, there's like this whole cache of sea urchin that have been sitting out in the sun, the California sun, for like 6 months, and all of that part of the process is gone already. So that's something that I recommend, is if you're working with urchin, get clean urchin, because the organic stuff makes it like 3 times harder to work with, and just get stuff that's been sitting out in the sun for a long time. And then this is something that's maybe more for pottery nerds, but when you buy commercial glaze minerals, they're being sold at 80 mesh, which is just a spec. It means that the mineral can fit through a sieve that has 80 little holes per square inch. So it's a really small particle size. But I was using 60 mesh, so I wasn't grinding it up as fine as a commercial or commercial whiting place would in mid-range firing, and then sometimes even 40 in high firing. And so this is just a note: don't do more work than you have to. It probably will melt. And that's the whole reason we just crush stuff up really small, is so that it's makes it easier to melt. It's like why you put a little piece of butter in the pan and not just a whole stick of butter in the pan, because stuff melts faster when it has more surface area. So that was also just a kind of cool moment for me as a potter, was to step away from this commercial standard that I had been given of, okay, this is how small a glaze particle needs to be, to then be like, well, does it really need to be that small? And then find out, oh no, it doesn't. Like, this is just a commercial industry standard for like, a really, really high quality product, which wasn't really what I needed. And then, so here, this is in Noyo Harbor, and you can contact the Noyo Center if you want to take urchin from this. But this is just like a beautiful cache of urchin. If you see it in Noyo Harbor, just go look at it, because it is so cool to see like thousands of pounds of urchin just all in these crates. So there are a bunch of conservation efforts going on the California coast, mostly volunteer divers are going into the water, and sometimes they remove them. I think they're removing them from the water at Portuguese Beach, and then sometimes they just smash them. So yeah, it's kind of an interesting question too, like, should we actually be taking all of this urchin out of the water? Like, we're taking more calcium out of the water. Like, what's our whole goal here? Does this disrupt the ecosystem at all? But there is this huge cache of urchin that is really great for artistic purposes. And so the whole urchinware line, I went with this urchin inspired form. So as you can see, here's a little dish. These are, I was making, and then here's actually a sea urchin. And I also really just appreciate the beauty of the sea urchin. It has this pentaradiate symmetry. It has it has 5 different sections, which is why all of the art I was making were pentagons. And you can see really clearly that it's a cousin to the sea star here. I think this little piece really brings it up. But I saw this diagram once and I haven't been able to find it again. But somebody was like postulating that sea urchins have a really similar early lifestyle to sea urchins, where if my hand is a sea urchin, imagine it's a little bit more symmetrical, but then you take all of the different arms of a sea urchin and get them to curl up, then that's how you get this test shape. And you can really, I feel like, see that here. Like, imagine, like, this is the tip of a sea urchin arm, and if you unfolded it all of the way, and if you unfolded this all the way, and all of these all the way, you would get this like this perfect star shape. But then the sea urchin kind of fills in the gaps with more calcium carbonate plates. So I also just think they're like such a beautiful form. All of these little mounds that are on them, that's where their spines are attached. They have these little ligaments that attach the spine to the mound, and then it's actually just a ball joint like moving around in there. It's so cool. Definitely go to the Noyo Center and like hold some sea urchins. I love watching them move. They're so interesting. The way they walk, like just moving on all these different ball joints, kind of crawling along the seafloor. So I took this urchin-inspired form, and form wasn't really the focus of my residency. I was there to think about glazes. So once I found a form I liked, I just kind of stuck with it, because I needed to make a lot of pots to do a lot of experiments. And I really like the way the urchinware stuff looks. I think it's pretty cute. It's like fun to drink out of something that looks kind of like a sea urchin. And it's different than your everyday circular mug. So here's the urchinware that I made. These two on the right are kind of its final form. Like, I switched to this lighter color clay body and I started making the mugs like shorter and wider, giving them even more of an urchin-esque shape. And then here's a great picture. This is like my ceramic urchin baron. So I took all of my urchinware mugs that I had and just put them all together, just picturing an urchin baron that I had made. And I really just kind of, out of my own personal interest in coffee, like chose to make coffee sets, and just rein in the scope of the project because I was only in California for 2.5 months. So I made these pour overs. I made 2 different color of cone 6 mid-range glazes, and then I made a couple of different designs of carafes. That this one's definitely my favorite with the bulk kelp on it. And then if there's any potters, you're welcome to screenshot this. This is the recipe for the urchin white glaze that you're looking at. This is on top of all of the urchinware. You can see here, urchin, this is where whiting would normally go in the glaze recipe. It accounts for 11% of this particular recipe. And yeah, it's like a really classic studio glaze. Like, you'll find this glaze a lot of places, except instead of using urchin, they'll use whiting. And yeah, I hear some people kind of like call it Elmer's glue white, or like buttermilk. But just a really, I think in my mind, like a really good solid glaze, like nice to have in your kitchen. It's a really, yeah, works really well. And then, like Margaret was asking, to make it purple, I just put this stuff called a mason stain in it, which is a pretty new invention. It's like this colorant that's been encapsulated in glass and it doesn't melt. So it really is changing like how people think about mid-range glaze coloring. But that is a topic for another time. And so my final finding of like, can you use urchin as a replacement for calcium carbonate? I honestly would say it's not really worth it. And maybe somebody will use it in concrete. And the reason I say that is because calcium oxide, which calcium carbonate decomposes into, is known as quicklime, and it's a major ingredient in concrete. I don't recommend it for glazes because as potters, we are very particular about what's going into our glazes. And so any potential source of contamination kind of just takes it off the market as being like, oh, could we get a pottery distributor to start selling urchin instead of limestone? But this is maybe people could use it in concrete, and you know, they're probably less picky about what exactly is in the concrete. But then this aside here, because of how capitalism works, terrestrial sources of calcium carbonate will probably always win. They'll probably always be cheaper. And then also the urchin whiting smells really bad. You have to like put it through this 6-month long process of cleaning it or drying it. And I think that also probably just doesn't really fit into the way our economy currently works. So it was a really interesting exploration. And if anyone owns a concrete company, definitely get in contact with the Noyo Center and try to use their urchin and see if you could use it in there. Okay, so now I'll go into like the second half of my residency where I was thinking about ocean chemistry and glazing. So like I showed in a previous slide, we were doing wood firing at Cobb Mountain Art and Ecology. And here's a little table I found of what is in the wood. So wood firing is really special because the wood ash settles onto the surface of your pot and it melts and it forms a glazed surface on its own. And so wood ash is like a perfect glaze because all of these are things that we now take from commercially mined sources and put into glazes to make into glaze. So silica, like I mentioned, is a major part of glaze. Calcium, they form crystals. All of these melt really well together at high temperatures. So this in itself can be a glaze, is wood ash. And then here is drawing the tie to ocean chemistry. Here are the 6 most abundant ions in seawater. And there's actually quite a bit of overlap. There's magnesium and calcium and potassium. Sodium isn't on this list of what's in from wood firing, but definitely sodium is used in glazes a lot. Sulfate, you can get really interesting orange crystals from sulfur. And so I was kind of thinking like, okay, instead of making glazes out of all commercial sources, like how much can I find from just hand harvesting? So I was going to the ocean and I was bringing back ocean water to the studio, and I was going to the ocean and I was getting kelp and bringing kelp that had washed up on the beach back into the studio. And I obviously already had a ton of urchin. And so I was trying to make novel pots with this. So the first glaze that I made with the sea urchin, usually when you make a glaze, you mix it with water and you have this like kind of thick liquid, like maybe a very viscous syrup. And so I made my glaze and I left it overnight, and I came back and I had like this bucket of sludge. And something that I hadn't taken into account is the fact that seawater has a lot of microorganisms. And even when you turn that seawater into a glaze, those microorganisms are going to continue doing their thing. So I think like I made this like perfect environment. I don't know if a bunch of microorganisms reproduced in it or if they drank all of the water. But basically my glaze like totally got turned and like sucked up into this thick sludge. So then I did some more emailing. South of the bay, south of San Francisco, there's these huge Cargill salt flats. And so Cargill, the company, is like evaporating seawater and taking the salt and using that, and then refining it and turning it into table salt. But I emailed them and I was like, hey, can you give me like 5 pounds of unprocessed sea salt? And turns out when you have like a good story behind it, people are pretty willing. So I drove down there and got like these huge bags of this like beautiful crystalline sea salt that then I started working with this seawater concept, except taking the microorganisms out of the system. So here is pictures of this. I really only got to do one firing where I was experimenting with this, but it was a really amazing experience. So here's this smaller wood kiln. We're going to use this for a salt firing. And so in salt firing methods, you introduce a bunch of salts into the kiln at a really high temperature, and all of those volatilize and settle onto the surface of your pots. So you can see in there one of my experimental pots, this little guy with some kelp wrapped around it. Then it sat in a kiln for 2 days where we fired it to 2400 degrees Fahrenheit. And we're constantly feeding wood into it and put a bunch of salt into it. And I made a handful of experimental glazes that I put into that kiln. So here's the first one. This is a really great example of what happens when you don't have enough silica in a glaze. So you can see like this piece right here is like, it's like chipping off of the pot. It doesn't have this glassy surface to it. It actually doesn't even hold water. If you put water into this pot, it's still porous. And this was an experiment I did. I found a clay up in Humboldt County that I harvested off of the beach. And so I took 50% of that clay and put it with weight by 50% urchin and just mixed the two of them together and put it on the surface of this pot. And so the main thing I'll note about this is that there's not enough silica in it, which is why it looks like this. But the colors are pretty interesting. And I don't know where those come from, something that's in the clay body. So then here's another one. This is an urchin clear glaze I made. So this was a cone 10 glaze. It was basically really similar to my urchin white, where I took a regular glaze recipe and I swapped out the commercially mined calcium carbonate and put urchin in it instead. And then I wrapped this stipe from a giant kelp around it and put that in the same kiln. And this is just like, when this came out, it was such a cool moment for me, because as you can see clearly, like the kelp stipe, just whatever ions are in the stipe got stuck into the glaze, and it retained its character on the surface. And this is a really interesting thing chemistry wise, because it stayed green, which is almost never what you expect to happen in ceramics, is for something to come out the same color as what you put it in. But what I'm guessing is that this stipe itself had probably some calcium in it, and possibly some potassium. Those are two minerals that make, or two ions that make green crystals. And then this clear glaze in a non-wood firing comes out a lot clearer. But as I was saying earlier, all of that wood ash and probably the soda, the salts that we introduced halfway through the firing, they also gave it this like really rich crystalline surface. Here's another one. Now this kind of brownish mottled surface is a lot more characteristic of wood salt firings. So this one I had no glaze on. You can see the before picture. I wrapped the stipe of a giant kelp around it, and then I put some Turkish towel inside of it. And I also put some of those like really big salt crystals inside of it. And this is something that's like so great about kelp, is the fact that it just dries in place like this. Like I went to the beach and I got some kelp and I brought it back in a bucket and I wrapped it around my pots, and then I let them sit overnight. And when the pots dried out, the kelp just like has these really great plastic properties to where it just stayed exactly where I put it. Like I didn't have to glue it on it or anything. Just appreciation for kelp. I feel like it should show up more in our daily life. But then you can see this one is like probably my favorite pot I've ever made. The fact that the kelp burned so nicely onto the outside of this pot. And this is interesting because on this side, I'm like, okay, like there's probably calcium and potassium in the kelp. And then on this slide, I'm like, oh, it's orange, like there's probably sulfur in the kelp. So it's just, more research really needs to be done on exactly what's going on here. But yeah, it just went all the way around so nicely. Even this is like pretty interesting. It like looks like there's still some like the kelp. It's not kelp, like I can't pick that off, but it definitely, like the shape of the glaze like has the shape of the kelp in it. But it's like been fossilized somehow through this process. And then this is sometimes things melt, which is definitely something to expect when you're working with experimental materials. So this is kind of like a terrifying mistake, because when something melts this bad and sticks to the kiln shelf, it can possibly ruin the kiln shelf. But I was not expecting this to melt. But I do remember I soaked this pot in salt water, and then I also put some of these big salt rocks on the bottom of it. And I think that what I did was introduce way too much flux into the system, so that even the clay body itself melted. So that's what this is like, this like molten clay glaze mixture at the bottom of it. And then I just thought this was really beautiful. Like when I pulled it off of the kiln shelf, there were all of these colors on the bottom side of it. that had probably formed in an oxygen poor environment, because if there's these bubbles and it's sticking onto the kiln shelf, there's no oxygen in there, which is something that potters like to play with a lot, is reducing versus oxidizing environments. And so I'm guessing the lack of oxygen is what created all of these colors that are on the bottom here. This was really a really cool glaze to make. I took how I usually make my urchin clear, except I mixed in a bunch of salt into the water. So I like made fake ocean water. And then I fired this pot, which this one also kind of melted, which was a bummer. But there's just some really fantastic crystals in here, that I think is all coming from the salt. Like this really dark green color and the way that like the white's showing up here. Just really, really cool to watch. And then here's a really good picture of my big salt rocks that I got. And then this one just totally melted. This was that local clay that I mentioned earlier. I got it from a beach in Humboldt County. And it totally melted, like could not withstand the heat that was in that fire. But to any like aspiring wild foraging potters out there, this is a really great example of why you use a little catchment bowl or a catchment plate. Because yeah, you really don't want stuff melting onto the kiln shelves. It's pretty bad for them. But when this piece melted, I had this other pot underneath it that I knew would make it through the firing, and so it actually didn't do anything except for make this like kind of silly little piece of art. Yeah. I guess that's so that's the end of the part about exploration. And then I'll just say, kind of like as my little soapbox, it's just how important it is to be thinking across disciplines when we're approaching conservation problems. It's really like nothing else. Like you need policy, you need science, you need ethics, you need economics, you need artists. Everybody has to be approaching this problem from wherever our discipline can stand from. And I think the more that you try to make connections, and the more that you think in different frameworks, the more you come back to your other framework, and you're gonna have new insight to it. Like I've been programming for the last 8 months. I haven't been making any ceramics. And I'm really, really excited to come back into the studio, because I think everything, if you allow it to, is a generative process, and is gonna inform your art practice. Yeah. And yeah, here's just some really beautiful pictures of the California coast. So with that, I'll say thank you. Here's my contact information. You're welcome to email me, especially if you want to collaborate on doing some urchin modeling. Maybe you've got some of the math figured out in ways that I don't yet. And anything else.
Well, thank you, Leila. That was super interesting. And really, it was a really great sort of insight into the journey you've taken from all of your, sort of thinking in different disciplines. So that was really neat.
What's next for you?
That's a good question. Like artistically, or with
Oh, the mix of using art and scientific thinking for conservation. What are you thinking is next to kind of feed your soul with art, and also try to come up with ways to help heal the environment?
Yeah. Well, there's a couple of things I've been dreaming of. Is kind of like going the opposite direction of this, and like finding some places that are like toxic dumps, places that like humans don't really go anymore. There's oftentimes really heavy metals in those places, and those are really interesting for pottery. So it would be very interesting to me to like go there and see if I could use some of those like heavy metals that are sitting at the bottom of contaminated lakes and try to make art out of that. But I feel like I have to be a lot more careful about it, because it is like the idea is to step into contaminated spaces intentionally. With sea urchins, I'm really interested in modeling them more. So that little model I showed was kind of just scratching the surface. And I would love to find ways to make that be something that, it's a projected art exhibit. Like people are looking at the urchins moving, and the interactions, and feel like they can interact with it. The kind of thing that you would find in like a science museum like Noyo Center.
I'm sad to see that you wouldn't recommend using Urchin as a source for glaze. This is a bit of a bummer, but we are working with people who are trying to use it in cement, and we're working with people who are trying to have you met Verge Khan yet, who's trying to use it for engineered stone and some other products too. She's working on some biomaterials using the Urchin test. So that we're hopeful that we'll find somebody that can really put it to use. For those of you who don't know, right now everything that we take out of the environment, we're probably composting. I mean, the calcium is great for our soils as well. So, but anybody who has a use for these things should reach out. And I think Leila and I were both talking before we started that the restoration effort that TNC is leading at Portuguese Beach and Mendo Bay, they have a forum if you want to request some urchin. So they're bringing out a bunch of urchin and just making them available for people just like Leila who want to try to experiment with them. And so I don't have my hands on the form right now, but you can reach us at info@noyocenter.org and we'll send it to you. But with that, I will say thank you so much, Leila, again, for not only talking with us tonight, but for all that you're putting into your interest in conservation and especially the kelp forests and the problems we're having in the North Coast. I hope you must have gotten to dive in Monterey kelp forest by now, right? Okay, good. But it's still not the same as bull kelp forest.
Yeah.
So,
yeah, they're beautiful.
Oh my gosh, absolutely majestic. So thank you all for joining. Again, if you feel like you can donate something, please do support us or any of the nonprofits in your life. Everybody needs a little help. And I want to thank Wendy for organizing this, our board member and volunteer coordinator, as well as Peggy, who is a science talk committee member. So with that, I'm going to say thank you all very much. Have a lovely evening. Go out and enjoy the beautiful fog we have tonight.
Thank you so much. This was really fun for me.
Good.
Thank you. That was great. We really
you.
appreciate you doing this.
Yeah.
Thank you.
Thanks, Leila.
Alrighty. Good night, everyone.